So let's take a look on this chapter 7. So we have electric fields. First point, the electric field of a charge is the space around the charge in which an electric force due to that charge is experienced. So let's look at the pictures to understand electric field. So electric field is the region here, around the charge. Okay, so you can see some lines with arrow. That is the electric force. So what is meant by electric force? You can see it is coming out from positive charge and it is going into the negative charge. So the electric force with that particular kind of arrow is actually the electric force experienced by the positive charge. So electric force on positive charge. Imagine that if you put a positive charge somewhere in this region. Okay, so you should expect it follows the arrow, the line, the electric force. So which means it will move this way to the negative charge. As you know, positive and negative attract each other. And you should expect it goes away from the positive charge. As we know, positive and positive charge repel. So that's why this arrow, which is called the electric force, is the force experienced by the positive charge. Okay, so likewise for this electric field, as you can see, both are positive charge. So the electric force is coming out from the positive charge. So if you have another positive charge that put in between, so what happens is repulsions will happen. You know, there are light charge. So repulsion, they will follow the arrow, so they will go that way. Yeah, follow the arrows. So that is the electric field and the electric force. Now, next point, this point, directions of field lines shows the directions of the field always from the positive charge to the negative. So as you can see, the arrow from positive to negative. Okay, next point, higher density of lines shows a stronger regions of field. Okay, so higher density is region around here. You can see many lines in that region. Lower density is region which is far away, so you can see less lines. So example is like there. So you can see less number of lines for the electric force. Okay, so which means when it is closer to the charge, the density is greater. So when it is further away from the charge, the density is weaker, or the density is lower, showing that the electric field there is weaker. Okay, now we move on to 7.1, Coulomb's law. Any 2-point charges exert an electric force on each other that is proportional to the product of the charges and inversely proportional to the square of the separations. Okay, so that is Coulomb's law. So for example, you have a positive charge and a negative charge. So you multiply their charges, Q times Q. Then you divide by the distance between the positive charge and the negative charge, and you square the distance. Okay, then of course you have to divide by 4 pi epsilon naught also. Then you will get the electric force. Okay, you will get the electric force. So if they are if they are different charge, opposite charge, they will attract each other. If they are like charge, they will repel each other. So if they repel each other, the force that we get will be a positive value. If they attract each other, the force that we get will be a negative value. Okay, so if you remember chapter 2, we have the gravitational field. We have something similar. where that time when we go through the formula, uh, we have the Newton's law of gravitation. Newton's law of gravitation is very similar to Coulomb's law. So it is about two objects that attract each other. So I put it at the side here as reference or comparison so that you can see something. So Newton's law of gravitation, we have F proportional to m over r squared. So we have this formula which is very related to Coulomb's law. So after that, if you don't want the proportional signs over there, you can change it to equal to gmm over r squared. So we will get the force. Of course, it is the force that attract the object with mass will attract each other. So for example, between the sun and the earth, they attract each other. So the similarity between these two is we multiplying we are multiplying the masses of the objects to get the force and divide by the square of the distance. So here same also, we are multiplying the charges of the two point with charge, the 2 point charge, and then divide by the separations with power 2. So that is the similarity. Yeah? So you see it looks more or less the same, the formula. Then we have the constant, which is g over here, but for this case the constant is 4 pi epsilon naught at the bottom. Okay, so epsilon naught, let's discuss on this. Epsilon naught is known as permittivity of free space. The value is 8.85 multiplied with 10 to the power of negative 12. This is the unit. The unit can be force over meter. Okay, so we have two options here. So this value is given in the data booklet on the front page of the exam paper. So you can just look at that. Okay, so now let's move on. 7.2, electric field of a point charge. Okay, electric field. So electric field strength. We are going to care about the electric field strength. So the first point, electric field strength, force per unit positive charge. So from the definition itself, we will understand that they are talking about force divided by charge. Okay, so electric field strength is force divided by charge. Force divided by charge. So based on the definition. Okay, so imagine that you have this formula, which is the formula that represents the force. So if you take this formula, you divide by charge, divide by Q, that means this Q will be removed. And if you remove that Q, you will get this formula then. Okay, you get this formula. The Q has been removed compared to this formula. Okay, so that is the formula for electric field strength. Electric field strength. So electric field strength, we have to know the unit also. So the unit of electric field strength, so either you do Newton per Coulomb. As you can see, the definition is force per unit positive charge. So force Newton divided by charge Coulomb. Or the other option is you can put watt per meter. Watt per meter. So watt per meter, of course, this formula we learned last time in AS physics. That time we have V over D. F equal to V over D. That is the formula for plate, for plate, electric plates. So over here it is a point charge. So the plate that I mean was is something like this. So you have the electric plate like this. Then the distance is here. Let's say here is positively charged, the other side is negatively charged. The D is here, the distance. So we have F equal to V over D. So the formula comes from there. This is for electric plate. But now we don't use electric plate formula so much. We focus on a point charge. A point charge, something like this. One point with charge, and then the formula that we use is this: E equal to Q over 4 pi epsilon naught R square. Okay, so let's compare with chapter 2. So chapter 2, that time we learn about the gravitational field strength. Gravitational field strength is very much related to this. Gravitational field strength is known as G, is known as force per unit mass. Force per unit mass. Okay, so imagine if you have this formula based on Newton's law of gravitation, you divide by m, right? So you will end up with G equal to Gm over R square. So this is related to the electric field strength here, but we call it gravitational field strength. Okay, so let's move on. Again, you can see relationship between the formula here and the previous formula. Okay, now the next part, 7.3, electric potential. So the first point, electric potential, and the point is the work done in bringing. Okay, so there is a missing G there, bringing unit positive charge from infinity to that point. So from a place which is very far away to a particular point, then you will get the electric potential. So electric potential is work done. It's work done. So for example, let's say you have a point charge here. So you are trying to bring another point charge, not from this point, but from infinity, very far away, to this point A. Okay, so from infinity, which is very far away, to this point A, the work done to do this, how many joule you spend to bring this over here, that is the electric potential. Okay, it is the work done. Okay, so we look at the formula then. Okay, as you can see here, work done equal to V times Q. Okay, so I'm going to change it to small letter q. It will make more sense later. Work done equal to V times Q. So maybe you're wondering, where is this formula coming from? Actually, we learned it last time in this way. We learned it as the definition of potential difference, which is work done per unit charge. So work done per unit charge is the definitions for the potential difference, and then we rearrange the formula. Then we get W equal to VQ. So beside that, we also know this basics formula for work done. Work done equal to force multiplied with the distance or the displacement. Okay, work done equal to force multiplied with displacement. So because of that, we can equal the work done, the two equations here. So we have VQ equal to FD, imagine that, and then we bring the Q to the right hand side of the equation and divide, and we end up with this formula. Okay, so this formula, we have Q at the bottom, and now we replace the F. So we replace the F with the Coulomb's law formula. So imagine that we replace it. Okay, let's say I write down. You know the Coulomb's law, the force is equal to Q over 4 pi epsilon naught R square. So that is the force, and then the D I put outside here, and then divide by Q, I put outside here. So we have to know what is meant by that D. The D is actually the R. Okay, so that's why we can cut away. We can cut away the D and the R. Okay, so D is equal to R, so we can cut it away. And then we can cut away the Q also. So that's why at the end you have Q over 4 pi epsilon naught R. Okay, so that is the formula for electric potential. Electric potential for a point charge. So you have to remember how to derive it. Okay, how to derive it. Now, okay, so let's compare to the chapter 2. Chapter 2 we have gravitational potential. Gravitational potential is phi. So the definition is the same. It is also the work done in bringing a unit mass from infinity to that point. So that is the definition of gravitational potential. And then the formula is minus Gm over R. So you will realize that it is more or less the same also. So you can see the R is no R square anymore. As you can compare, this is R, this is also R, and then the mass remain there. So the Q remain here, the constant 4 pi epsilon naught remain, and then here the G remain. Okay, so of course for this case we have a negative because it is always attractive for gravitational potential. Then how about electric potential? Is it positive or negative? So we put it in this way. Okay, positive or negative. We have a few situations to discuss about. So let's say if it is okay, positive or negative. Let us discuss about this. Okay, positive or negative. So as you can see, gravitational potential is negative because it's attractive. So positive or negative, we have two situations. So when a positive charge is brought towards a positive body, which is also positive charge. So it gains V, electric potential. Okay, so then the graph will be like this. That means positive. That means V is positive. Okay, the graph is like that. V versus R. Okay, so this is the first situation. That means if it's positive and positive, then it will be positive. Positive charge with a positive charge bring nearer to another positive charge, then the V is positive. Okay, it's positive. So likewise, if it is negative and negative, so then the V is positive. If the charge is the same, then the V is positive. So the second situation, when a negative Q is brought towards a positive body, which is positive Q, so it loses V. So V is negative. Something like this will happen. The graph will be like this. V versus R. the graph is going down. So compared to chapter 2, right? Chapter 2, we only have this situation. Phi versus R, the graph is always going down because the force is always attractive. But for this chapter, we have repulsive force if they are light charge, and we have attractive force if they are unlight charge. So in that situation, right, if they are light charge, we follow this one, the V is positive. If they are unlight charge, the V is negative. Okay, so now let's move on. Yeah, the potential the potential difference between 2 points A and B from an isolated charge Q is defined as work done in taking a unit positive charge from B to A. From B to A. Okay, so that is called the potential difference. So electric potential difference. Okay, now let's see how we understand the formula. So to find potential difference, we are using this formula for 2 times. Okay, we are using this formula for 2 times. Basically, we put it in this way. We are using V final minus V initial. Okay, V final minus V initial. So let us put it down here. This is actually the final minus the initial. V final minus V initial. Okay, so what is V final? So let's take a look. V final. Okay, I bring it down here. So initially it stay at B. Okay, initially it stay at B, and then finally it go to A. Finally it go to A, from B to A. Okay, when it's at B, right? So we use this formula. So imagine we have Q over 4 pi epsilon naught R. The R is B. Is B, yeah. That sorry, final is A. Okay, it's A. Final is A. Okay, initial Q over 4 pi epsilon naught B. So that is initial. Okay, then after that we factorize. Q over 4 pi epsilon naught 1 over A minus 1 over B. Okay, so supposed to be like this instead of this. Okay, now let's look at the graph to understand it. We have a positive charge move towards another positive charge. So of course we will take this graph. Okay, we'll take this graph. So the capital Q, right? This capital Q is staying in the middle. Okay, that's the positive Q. Okay, it's staying in the middle. Okay, let's say point B is somewhere, yeah. Okay, just somewhere here. Somewhere here. Point A is somewhere here, nearer. Okay, so let's put it in the graph. Point B is here. Point A is here. So from point B, it moved to point A. So you should expect increase in V. Yeah. Okay, increase in V. Okay, it gains in V. Now let's look at the formula. 1 over A. So 1 over A, as you know, A is nearer. So your A should be smaller. 1 over A should end up with a bigger answer because you divide by a smaller A, so the fraction should be a bigger value. Okay, So compared to this, 1 over b, b is further away. So b should be a greater value, and then 1 over b, you take 1 divided by a big value, you should get a small answer. So it should be a small answer. Okay, so we have a bigger value. 1 over a is a bigger value, minus with a smaller value. So you get a positive answer that fulfill with the statement here saying that it gains in electric potential. Fulfill the graph also, it gains in electric potential. So that's why we have to take final minus initial. Okay, final minus initial. Not like this, not like this. Okay, but like this. And then it will fulfill the graph at the same time. Okay, so this one I just cut lah. Should be the other way around. Okay, now next point, VAB. VAB. So again, if you want to look at this statement, right, we must have a condition. The small q if q is positive, small q must be positive, and then you can use this, then we can take this statement. Okay, so let's look at the point again. VAB is equal to the gain in electric potential. So as we have discussed, it move up, the graph move up. Okay, so gain in electric potential energy. So now they start with energy, right? They put energy. So you have to know electric potential and electric potential energy is different. It's slightly different actually. Okay, so if Q is positive, so and loss if Q is negative. Okay, so let's understand this first. Electric potential energy. So the symbol that we use is EPE or EP, electric potential energy. So if the small q is positive and the capital Q is also positive, so it's basically this situation. It's basically this situation. The the only difference is just now this is electric potential, right? Now this is electric potential energy. So we have to know the difference between electric potential and electric potential energy. Okay, so I put it at the side here first before we look at that statement again. Okay, so put it as a note here. Electric potential, which is V, the formula is Q over 4 pi epsilon naught R. That is electric potential, which is work done to bring a unit charge from infinity to a point. Now, what is electric potential energy? Okay, electric potential energy, which is equal to EPE, is actually equal to V times Q, and we have Q over 4 pi epsilon naught R. So this is electric potential energy. So you will realize the difference is there is a multiplication of small q to electric potential. You multiply with small q, and then you get electric potential energy. Okay, so the small q of course is a constant, and it won't affect the graph too much. It's just a constant. So what am I trying to say is, if I change the graph, instead of the vertical axis is V versus R, right? So if I change it to electric potential energy. So if I change it to EP versus R, basically the graph will be the same, okay, if both are positively charged. So likewise, if I change it to EP, then of course, if the if the small q is negatively charged, the capital Q is positive charge, then the graph will still looks the same, which means it goes down. Okay, it goes down for this situation. So it will be the same graph, and the concept will be the same also. If both are positive, you bring from you put it nearer, then they will have increase in EP, increase in EP. Yeah. So that's why this point makes sense here. VAB is equal to the gain in electric potential energy. Gain, because you move from here to here, right? You move from here to here, there is an increase, there is a gain here. If Q is positive, if Q is positive, if Q is positive and the capital Q is also positive, then it will be a gain if you bring nearer, but it will be a loss if Q is negative. So if they are opposite charge, you follow this, they will go down. They will go down. If they are opposite charge, they will go down as they attract. So in general, if positive charge move in direction of electric field, move in direction of electric field. So what is that? You have to think about it. What is direction of electric field? Okay, so let's say I clarify this direction of electric field. Okay, so I need a bit more space here. So this arrow adjust a bit. Okay, direction of electric field is like this. So imagine you have a positive Q, you have a negative charge, positive charge and negative charge. So we draw our electric force from positive to negative. This is direction of electric field. Which is this one? The electric field is positive to negative. So now let's say I have another positive charge. Okay, another positive charge. I have another positive charge. Okay, let's say I put different color. Okay, another positive charge. If I have another positive charge which move in the direction of electric field, which means move to the negative charge. So logically, if you understand what I said, right, so you should think of, okay, which is this graph then, because it's positive to a negative, positive to negative, which attract. So if attract, they will follow this graph. So its electric potential energy will decrease. So decrease. You can put it here. You can put it this way also. Imagine the negative charge is staying in the middle. Staying in the middle. The positive charge, which is this one, is approaching it from the left hand side. So it will decrease in electric potential energy. Okay, it decrease. So okay, I label it in this way. This one I call it A. And then in terms of graph, A is here. Okay, A is this one. Okay, I put blue color there since I'm using blue color there. So I put blue color A. Now, second point, let's say I call it B. If negative charge move in direction of electric field, its electric potential energy will increase. Okay, so they are trying to say this negative charge move in the direction of electric field. Okay, as you can see, they are like charge, they are like charge, same charge, negative to negative, so they will repel, So if they repel, right, so basically you have to follow this graph. This graph is for repellent. Okay, so from left hand side, you are going to another negative charge so that we repel. So something like this will happen. Okay, so I just draw out and label. So this is B. Okay, so electric potential energy will increase, as you can see over there in the graph. Now next one, if charge accelerated in the field, its electric potential energy will be converted to kinetic energy. So electric potential energy is VQ. It's VQ. We have discussed it here. So the electric potential energy is changed to kinetic energy. So that is half mv squared. Okay, so meaning that we better put it in this way. There will have a decrease in EPE, which causes the increase in kinetic energy. So decrease in EPE is equal to the increase in kinetic energy. Okay, so now let's see the other graph here. So this graph is electric potential versus R. So electric potential versus R, we already discussed is V versus R, right? So the graph is already given here, V versus R. I put both sides, and this one they put one side. What is the difference between one side and two side, like what I have drawn here? So the difference is, if I put two side, right, that means if your positive Q is in the middle, and if you have another positive Q, which can approach from right hand side to the positive Q, or you can also approach from left hand side to positive Q. No matter which side you approach, right, you will get an increase in electric potential. So if the positive Q approach from the right, so it will come along this way. If the positive Q approach from the left, then we follow this way. So no matter which side, they will increase. So that is the reasons why I put two sides. Okay, I put two sides. If they put one side, of course, they don't consider approaching it from the left. They don't consider approaching it from the left. They just consider approaching the positive capital Q from the right. The small q approach from the right. They ignore the other side. Okay, so let's see what information is given here. Okay, so we can count the gradient of this graph. Of course, to count the gradient, imagine I have to draw a tangent. Let's say I want to count the gradient here, and then I draw a tangent, and then draw a tangent. Okay, then you have to get the change in V. The change in V is here. The change of R is here. Okay, then that will be the gradient. That will be the gradient. Of course, you can use coordinates. You find this coordinate, then you find this coordinate, then you use the gradient formula, and then you get the gradient. End up with a negative value, because the line is going down, right? So the gradient is negative. So what am I trying to say is, you get a negative gradient, and you put another negative to make the value positive. We want positive value. Okay, we want positive value. So the gradient itself is already negative value. So we put another negative there to make it positive, and that value is equal to E. Is equal to E. What is E? Electric field strength. Okay, electric field strength. Okay, electric field strength, which is this one, E. Okay, so logically it is true, because you are taking V divided by R. As you can see, the V formula is here. V equal to Q over 4 pi epsilon naught R. So finding the gradient is same with dividing with R again. Dividing with R again, then you get R square. So if you get R square, of course, it will end up with R square, which is electric field strength. Okay, R square. So meaning that if you have this graph, you go and find the gradient. The gradient is negative, so that's why you put another negative there to make it positive. Then that value is the electric field strength. Okay, electric field strength. So it is a relationship between the previous one with this one. Okay, now let's look at chapter 2. Chapter 2, the relationship. We need to build up the relationship, which will strengthen up our knowledge here and there. So, since you have electric potential, as in here, electric potential, then you should expect we should have gravitational potential. Of course, true, we have discussed that already, okay, which is up here, here, okay, this one. Phi equal to minus gm over r, gravitational potential. And we should have gravitational potential energy also. Of course, that is also true. Okay, gravitational potential energy. Okay, let's say I put it here as comparison, right? Okay, gravitational potential is negative gm over r. Gravitational potential energy, we use U. It is actually m phi, which is equal to negative g mm over r. So you will realize they are similar, They are similar in this sense where you have to take the charges and multiply. Here you take the masses and multiply. So the bottom is R. This is also R. Then there is a constant there. So this one have a constant also, 1 over 4 pi epsilon naught. Epsilon naught. Okay, that is the constant. So similar. It looks similar. Okay. Okay. So before we look at the question here, this question is about sphere also. So let's go through the theory of sphere. Okay, a sphere. Just now on page 1, it is about a point charge. Okay, a point charge. So now it is a sphere. So the difference between a point charge and a sphere is a sphere will have a radius, have a radius from the center, and a point charge is having no radius. Okay, so that's the difference, no radius. So the r in the formula is the distance between one point charge to another point charge. That is the meaning of r. Okay, so but here the sphere has radius already. Okay, let's see the difference. So we start from the first point here. A charge positive q on an isolated conducting sphere is uniformly distributed over its surface. Okay, so that means the charge positive q, right? This positive q, this is the charge. So they are distributed everywhere uniformly around the surface. Okay, so that's the statement. Now let's move on. Second point. Charge remains on surface and at all points inside the sphere, the field strength is 0. So they are trying to say that the E, the electric field strength, which is E, right, is equal to 0. Inside the sphere, there is no electric field strength. So as you can see our graph here, if we are drawing electric field strength, E, Okay, so in the middle it should be 0. So 0, this is inside the sphere. Inside the sphere, it should have no electric field strength. Okay, so why? So we need to know why. Why there is no electric field strength. Okay, so we need to know how to answer this. Okay, so I put it at the side here. Okay, reason. So because they said charge remains on surface. Charge remain on surface. As you can see here. Charge remain on surface. At the same time, it means the charges in sphere do not move. They remain on the surface. Okay, they are not moving. And how come the electric field strength is equal to 0? So we have to put it in this way. Electric field strength, right? Okay, electric field strength, not intensity. Electric field strength. If you still remember the definition, electric field strength, which where the symbol is E, it is force per unit charge. Force per unit charge. Force per unit charge is actually what is force. Yeah, it's force. So when we talk about force, right, we have some background knowledge. Force, Newton's second law, F equal to ma. This is our background knowledge, which uh, will make us understand. Electric field strength is just force. So force is equal to ma. A is acceleration. Now the sphere, the charges is not moving. If it's not moving, of course there is no acceleration. No acceleration, and hence no resultant force. No acceleration, no resultant force. Okay, so we should put it in this way. So no resultant force on charges. So no electric field strength in the sphere. So you have to take it in that way, or you have to explain it in that way. So why they are having no electric field inside the sphere? Because the charge is not moving. Okay, it's not moving. It remains on the surface. Okay, now let's see the next point. The next point they said, as there is no field inside the sphere, the potential difference from any point inside the sphere to the surface is 0. Therefore, the potential at any point inside a charged hollow sphere is the same as its surface. Okay, so what are they talking about here? Okay, so they are trying to explain. The V, the electric potential inside the sphere is the same as the surface of the sphere. Same. Okay, so they are trying to explain. Okay, so uh, one of the easier way to take it is by looking at the gradient. If you still remember just now, page 1, right? page 1, if I have V versus R, the graph is like this. If I draw one side only, it's like that. And then just now we discussed already the gradient. The gradient, you put negative gradient is equal to E. Is equal to E. Okay, so now when you come to this, you can apply the similar concept where if the E is 0, right? If the E is 0 inside the sphere, as we have discussed the reason here, if E is 0, then that means there should have no gradient. No gradient or zero gradient for this graph. Zero gradient for this graph means the graph is horizontal. It's horizontal. So we can take it by using gradients, or over here they are trying to explain also. They are trying to explain why. Okay? They are trying to explain why. So basically what they're trying to say is, they say same. The potential difference is the same. Okay? Potential difference at any point inside a charged sphere is the same as its surface. Okay? It's the same only. Okay? So why they are same? Because there is no field inside the sphere. There are no field inside the sphere, then the potential difference from any point inside the sphere to the surface is 0. Okay, so which means potential is the work done. Work done. Okay, potential is the work done to move the a charge from a point to another point. That is potential difference. Okay, but no work done is required there, because there is no potential, there is no electric field strength inside. So because of that, it remains the same. Okay, it remains the same. So you have to think of work done. It will help you to understand it. But the thing is, past year question, they don't ask this so much. They ask this. Okay, so they ask this a lot. They ask this. They ask you why the electric field strength inside the sphere is 0, but they don't ask this so much. So if they ask, you just follow this wording here. This wording here will be fine. Okay? It is related to the work done. It's related to the work done. So work done is there when there is electric field strength, but there is no electric field strength. So no need to do any work. So of course, there is no change in the work done, to bring the charge from inside the sphere to the surface. Okay, so that is what are they trying to say. Okay, now let's come back to the question here. The question on the left hand side is about sphere. Okay, so the first part, the maximum field strength at the surface of the sphere before electric breakdown, which is sparking, occurs is 2.0 times 10 to the power of 6 watt per meter. So this is the electric field strength. This value is electric field strength. So which is known as E. Okay, so I label this as E first. The sphere has a radius R of 0.35 meter. Okay, 0.35 meter. Okay. Calculate the maximum values of the charge that can be stored on the sphere. Okay, maximum value of charge. That means you have to count the Q. Okay, you have to count the Q. So we have E, we have R. Okay, so the formula is E equal to Q over 4 pi epsilon naught R. Okay, so R square. So be careful with the r here. The r for point charge is the distance from one point to another point. Okay, but for sphere, the r here, is the radius. It's the radius. So that's the difference. Now let's substitute with value. E is 2.0 times 10 to the power of 6. So we are looking for Q. 4 pi epsilon naught okay, then we get the Q 2.72 times 10 negative 5 Coulomb. Okay, so this is A. Now B, the potential at the surface of the sphere. So we use V equal to Q over 4 pi epsilon naught R 2.72 and negative 5 4 pi times 8.85 then negative 12 times R 0.35. Okay, then we get 7 times 10 to the power of 5 volt. So we are using the formula straight away for these two questions.